Welcome you all. I am Vanitha, Assistant Professor, Department of Mathematics, St. Joseph College for Women, Tirupur. Now I am going to explain about single valued function, polynomial function, rational function, continuity of a function. Single valued function. If f of z is defined in a set D and if for each z in D there is only one value of f of z of or exists, then f of z is said to be a single valued function. Here D denote the domain of f of z and R denote the range of f of z. Suppose D equal to A, B, C, etc., where A, B, C are some complex numbers. Then R equal to f of A, f of B, f of C, etc. Example for single valued function f of z equal to z squared. Cartesian form of z equal to x plus iy. So z squared equal to x plus iy the whole squared. So we get f of z equal to x squared minus y squared plus 2ixy. Suppose z equal to 2 plus 3i. Here x equal to 2 and y equal to 3. Then f of z equal to minus 5 plus 12i z equal to 2 minus 3i. Then f of z equal to minus 5 minus 12i. For each value of z, we get one and only one value of f of z. So f of z equal to z squared is a single valued function. A function is not a single valued, then it is called a multiple valued function z equal to x plus iy. Its polar form is r into e power I theta. Here r denotes the absolute value of z and theta denotes the argument value of z. E power I theta equal to cos theta plus I sin theta. So we write r into e power I theta equal to r into e power I into theta plus 2 pi. Example for multiple valued function. F of z equal to square root of z. Its polar form is r power 1 by 2 into e power I theta by 2. If z equal to 4 into e power I pi by 4, we get more than one value of f of z. First value of f of z equal to square root of 4 into e power I pi by 4, which is equal to 2 into e power I pi by 8. Second value of f of z equal to square root of 4 into e power I into pi by 4 plus 2 pi, which is equal to 2 into e power I into 9 pi by 8. For each value of z, we get more than one value of f of z. So f of z equal to z power 1 by 2 is a multiple valued function. Polynomial function. Functions of the form Pn of z equal to a naught plus a1 z plus etc. an z power n. An not equal to 0, where n is a positive integer and a naught, a1, a2, etc. an are complex numbers. Then Pn of z is called a polynomial in z of degree n. Example for polynomial function. So, f of z equal to z cube plus 6z square plus 3 is a polynomial in z of degree 3. Rational function. The quotient of two polynomials is called a rational function. R of z equal to p of z by q of z, where p of z and q of z are polynomial in z and have no common factors. Example for rational function. R of z equal to 1 by z, f of z equal to z by z plus 1. Continuity of a function. If f of z is continuous at z naught, then f of z at z naught exists. Limit of f of z at z naught exists and equal to f of z naught. Properties of continuous function. If f of z and g of z are continuous at z naught, then f of z plus or minus g of z, f of z into g of z, f of z divided by g of z, where g of z not equal to 0 or continuous at z naught. Composite function of a continuous function is also continuous. Now I am going to explain some problem in continuous function. First problem, show that f of z equal to z square plus 1 by z minus I at z not equal to I. F of z equal to 2I at z equal to I is continuous at z equal to I. From the problem, we get value of f of z at z equal to I is 2I. So f of I equal to 2I. Then we find the limit of f of z at z equal to I. Limit z tends to I, f of z equal to limit z tends to I, z square plus 1 divided by z minus I. Limit z tends to I, z square plus 1 equal to z plus I into z minus I divided by z minus I. We get limit of f of z at z equal to I equal to 2I. which is equal to value of f of z at z equal to I. Therefore, f of z is continuous at z equal to I. Second problem for continuous function. Check if f of z equal to real part of z squared by modulus z at z not equal to 0. F of z equal to 0 at z equal to 0 is continuous at z equal to 0 or not. First, we write f of z in terms of Cartesian form. Z squared equal to x plus I by the whole square. Real part of z squared equal to x square minus y squared, which implies f of z equal to x squared minus y squared by root of x squared plus y squared. From the problem, we get value of f of z at z equal to 0 is 0. Therefore, f of 0 equal to 0. Then we find limit of f of z at z equal to 0. That is, limit z tends to 0, f of z equal to, in Cartesian form, z equal to x plus I by. So we write x comma y tends to 0 comma 0 of x squared minus y squared by root of x squared plus y squared. On the real axis, we get the limit x tends to 0, x squared minus 0 by root of x squared plus 0, which is equal to 0. On the imaginary axis, we get the limit y tends to 0, 0 minus y squared by root of 0 plus y squared, which is equal to 0. Limit on the real axis equal to limit on the imaginary axis. So limit of f of z at z equal to 0 exists and equal to 0, which is equal to value of f of z at z equal to 0. Therefore, f of z is continuous at z equal to 0. Third problem for continuous function. If f check if f of z equal to z bar by z, z not equal to 0, f of z equal to 0 at z equal to 0 is continuous at z equal to 0 or not. First, we write f of z in terms of the Cartesian form. So we get f of z equal to x minus iy by x plus iy. From the problem, we get f of z equal to 0 at z equal to 0. Therefore, f of 0 equal to 0. Next, we find a limit of f of z at z equal to 0. Limit z tends to 0, f of z equal to limit Cartesian form of z equal to x plus iy. So we write x comma y tends to 0 comma 0 of x minus iy by x plus iy. On the real axis, we get the limit x tends to 0, x minus 0 by x plus 0, which is equal to 1. On the imaginary axis, we get the limit I tends to 0, 0 minus iy by 0 plus iy, which is equal to minus 1. Limit on the real axis is not equal to the limit on the imaginary axis. So, limit of f of z at z equal to 0 is not exist. Therefore, f of z is not continuous at z equal to 0. Thank you all.